In this video, we're going to implement the quicksort algorithm in C. So the quicksort algorithm can be used to sort an array of elements, among other things. And the quicksort algorithm is a very efficient algorithm that's actually widely used in the real world. That's in contrast to some algorithms like bubble sort. They might be useful for learning about algorithms, but they're not very efficient in practice, whereas quicksort actually is used in the real world. So first we're going to go over the algorithm and how it works, and then we'll implement it in C. So the first thing we'll do is go over an example here. Let's say we have the numbers from 1 to 7 in an unsorted array. So 6, 3, 7, 5, 1, 2, 4. The way the quicksort algorithm starts off is we select a pivot in the array that we're looking at. And we'll say for now that the pivot is always going to be the last element in the array that we're looking at. So in this case, it'll be 4. The next step is to partition the array around the pivot. What that means is that all of the elements that are less than the pivot are going to come before it. All of the elements that are greater than the pivot are going to come after it. So in this case here, we'd have 3, 1, 2, 4, 6, 7, 5. And at this point, the array is sort of sorted around this pivot here, in the sense that all the elements that are less than the pivot come before it, and all the elements that are greater than the pivot come after it. And now we have these two subarrays here. And if we could sort these two subarrays, then the entire array will be sorted. So what we're going to do is apply this same process to each of these subarrays in a divide and conquer type approach. So here with 3, 1, and 2, we would select 2 as the pivot. And then when the array is partitioned around 2, we would be left with 1, 2, 3. Then with this right subarray here, we would select 5 as the pivot. When we partition the array around 5, we would be left with 5, 7, 6. Then we partition the array around 6, and we would be left with 6 and 7. And so this is how we could apply the algorithm to sort the array. Now, all of these elements are being sorted in place. So if you imagine a C program, in the actual C program, in the array that's containing these elements, we would have 1, 2, 3, followed by 4, followed by 5, followed by 6, 7. And as each one of these recursive steps occurs, where we apply the algorithm again, that algorithm is being applied to a sort of constrained portion of the array with sort of a low and high index that defines the boundary of the portion of the array that we're concerned about. And that's what we'll get into next, is how to actually implement the quicksort algorithm in C. So the first thing we'll do is create the function prototypes for the different functions that we're going to need. Here I'll say void swap int star x int star y. And the swap function is going to be used to swap two array elements. Then we'll say void quicksort int array and int length. And the quicksort function is what we're going to call to actually carry out the quicksort. And we're going to pass it the array and the length of the array. Now to actually carry out the recursive steps of quicksort, we'll have a function called quicksort recursion. This function will accept the array as an argument, as well as a low and high int. So these arguments are going to define the portion of the array that we're applying the quicksort algorithm to. Then finally, we'll have the partition function. So we'll say int partition, int array, int low, int high. So the partition function is actually going to carry out the partition step of partitioning the array around the pivot. So first we'll make a test array. We'll say int a is equal to 10, 11, 23, 44, 8, 15, 3, 9, 12, 45, 56, 45, 45. And we've got 13 elements in that array there. And we'll call quicksort like this. We'll say quicksort a length to actually apply the algorithm. After we apply the algorithm, we're going to print out the array to actually make sure it's sorted. So we'll do that here as well. We'll say for int I is equal to 0, I is less than length, I plus plus, and we'll print out each element in the array one after the other. So we'll say printf %d space a at I. And then after all that is done, we'll print out a new line. So this loop here is taking I from 0 up until the length of the array. And we're just printing out the element in the array A at each index. And after all that's done, we'll print out a new line. So now let's actually implement these functions here to actually carry out Quicksort. First, we'll implement the swap function. So here I'll say void swap int star x int star y. And these parameters here are pointers. So we're going to dereference the pointers to actually go and change the thing that they're pointing to, which in our case is going to be array elements. So here we'll say int temp is equal to star x. So what we're doing is we're dereferencing x and we're getting what x is pointing to, and we're storing that value into temp. At this point, because we've stored the value that x is pointing to into temp, we can now safely overwrite the value that x is pointing to with the value that y is pointing to. So we could say here, star x is equal to star y. Now what we want to do is overwrite whatever y is pointing to with whatever was in x, or whatever x is pointing to. And that is in temp. So here we'd say star y is equal to temp. That's going to complete the swap of the values that x and y are pointing to. Next, we want to implement the actual Quicksort function here. This is going to be a bit of a wrapper function though, in the sense that it's going to make using Quicksort easier. I don't want to have the users of my Quicksort function have to call the function by giving an initial low and high value. I want them to be able to just give the array and the length of the array. So this function is basically going to be a wrapper to make it easier to use Quicksort. So here we'll say void Quicksort int array int length, and we'll call Quicksort recursion with the array. And what we're going to give as the low argument is the lower bound of the portion of the array that we want to sort. Now, initially, we want to sort the entire array, so it's going to be 0. The starting point is going to be the first element in the array. And the endpoint, the high value, is going to be the last index in the array, which is going to be length minus 1. Next, we'll implement the Quicksort recursion function. So here we'll say void Quicksort recursion int array int low and int high. So here's where we're going to apply the recursive divide and conquer process of the Quicksort algorithm. So first we'll say int pivot index is equal to partition array low high. So we call partition to actually partition the array given these bounds, low and high. And what it's going to return is the index of the pivot. What we're going to do is use this when we cut up the remaining left and right portions of the array where we want to apply the Quicksort algorithm again. So we'll say here, Quicksort recursion array low pivot index minus 1. And this is going to be the left portion of the array from low up until pivot index minus 1. Then we'll say Quicksort recursion array pivot index plus 1 and then high. This is going to be that right-hand portion of the array where we're going to go from the element to the right of the pivot onto the high element. Now, eventually this process of calling Quicksort recursion has got to stop. And we're going to stop it when low is no longer less than high. So long as low is less than high, we're going to keep applying these steps here. When this is not the case, that's when the algorithm is going to stop. So the next thing we're going to do is implement the partition function. And in some ways, this is the core step of the Quicksort algorithm, and it can be the part that's a little bit tricky to interpret. So I'm going to try to help with that. So here we'll say int partition, int array, int low, and int high. So our first step is going to be to get the pivot value. So the pivot index is just going to be high, because for now, we're going to go with the assumption that the pivot is always going to be the last element in the portion of the array that we're looking at. So we'll say here int pivot value is equal to array high. And this will be our pivot index, and this will be our pivot value. Now what we want to do is actually have all the elements that are less than the pivot come before the pivot, and all the elements that are greater than the pivot come after it. We'll write a loop to help us do that, along with a couple of variables to help us index the array. So we'll say here, int I is equal to low. Then we'll say for int j is equal to low, j is less than high, j++. Now inside this loop body, we'll do a check. We'll say if array at j is less than or equal to the pivot value, then perform a swap. So we'll say swap and array I and array j. And then increment I by 1. When this is all done, we'll say swap and array I with whatever is in and array high. In other words, the pivot value is going to be placed into the index of I after all this is done. Then when this is done, we're going to return I. And we're going to return I because that's where the pivot is. And we know that's where the pivot is because that's where we just put it here. When we swapped whatever is in array high, which is our pivot, with array I. So we know that's the location of the pivot. So that's why we return it here. So what's actually going on here? I think this can be pretty tricky to interpret. I think if you're trying to interpret how the algorithm works, this is probably the hardest part right here, what's going on. So let's go over an example using the numbers we're familiar with from the start of the video. So we've got 6, 3, 7, 5, 1, 2, 4, and we know that 4 is going to be our pivot value because 4 is the last element in this portion of the array that we're looking at. And then what we've got here is two variables, I and j, that are pretty important because they're determining where the swap is going to happen, as well as whether the swap is going to happen in conjunction with looking at the pivot value. So we'll just sort of informally keep I and j around our array element values here to represent where they are in terms of the index they're set to. Because I is initially set to low, as is j. Now j is going to be incremented after every iteration of this loop. I is only going to be incremented in the case where the element in the array at index j is less than or equal to the pivot value. So initially here, I and j are both going to be set to this low index value here, the first thing in the portion of the array that we're looking at. And then we check, is the array at index j less than or equal to the pivot value? In the case of 6, it is not. So j is going to be incremented by 1, and j is now referring to 3. Now we do another check. Is array at j less than or equal to our pivot value? 3 is less than or equal to 4. So at this point, the code inside this if statement here is going to run. And we're going to swap whatever is in the array at index I with whatever is in the array at index j. So we're going to swap 6 and 3 here. So we get 3 and then 6. And then I gets incremented by 1. So I is here now. Then we do another check after j is incremented again, right here, in the next iteration of the loop. And we do a check. Is the array at j less than or equal to the pivot value? 7 is not less than or equal to 4. So j is going to be incremented again to 5. Again, we're going to have that the array at j is not less than or equal to the pivot value because 5 is not less than or equal to 4. So j is going to be incremented again to 1. This time, the array at index j is less than or equal to the pivot value because 1 is less than or equal to 4. So at this point, we're going to do another swap with whatever is in the array at index I and whatever is in the array at index j. So we'd swap 6 and 1 here, and we get 1 and 6. And now again, I gets incremented by 1 again to here. And you can kind of see it happening already, that we have these elements that are lower than 4 over here, and these elements that are higher than 4 over here. So it's kind of already starting to happen. We're going to increment j again here. now j will be at 2. 2 is again less than or equal to 4. So we'll do a swap again with whatever is in the array at index I and whatever is in the array at index j. So we're going to swap 7 and 2 here. We get 2 and 7. And I would be incremented again to where 5 is. Now at this point, j gets incremented again, but now j is not less than high anymore. So j is no longer less than high. Because j is no longer less than high, at this point, we're done. But there's one more step here. At this point, we swap whatever is in the array at index I with whatever is in the array at index high, that last element, our pivot the whole time, right? So index I is right here. So we're going to swap 5 with 4. And we get 4 and 5. And look what we have. We have the elements that are lower than the pivot value over here in the left-hand portion of the array. We have the pivot value at this index here that I is referring to. And then we have the values that are greater than the pivot value in the right-hand portion of the array. And so we've done it. And at this point, that's why we return I. So when we return I here, we're now telling the quicksort recursion function, hey, here's our pivot index. And then the function can just call itself again and split up the remaining portions of the array like this. So this should actually do it. So we'll save this and give it a test. Now there's likely some kind of bug in the code because we've just written a whole bunch of code without ever running it. So we'll try to run it. We'll see what happens here. It says build succeeded and it looks sorted. So we've got 3, 8, 9, 10, 11, 12, 15, 23, 44, a few 45s and a 56. So we've done it. We've sorted our array with Quicksort. Now I want to do one optimization though. So one thing we've done here, we're using this last element of the array as the pivot each time. It turns out that this can be inefficient in some cases. So depending on the way that our data is sort of organized in the array, it's possible that it turns out that this is just a really, really bad pivot value to choose. So sometimes what people do to make the algorithm more resilient in the sense of remaining efficient, even if the data is suboptimal for picking the high value, is that they'll randomly pick a pivot value between low and high. So in other words, the pivot value could be anything as opposed to always picking this pivot value. And it kind of guards against this being a consistently poor pivot value to choose. So we'll actually do that. We'll actually pick a random pivot. What I'll do is include stdlib.h, which allows us to generate random numbers with the rand function included inside of it. I'll also include the time.h library so we can see the random number generator with the current time. So in the quicksort function, I'm going to first seed the random number generator. I'll say srand time null. So srand is going to seed the random number generator with a value. It's important that we seed the random number generator with a different value each time a program runs in order to ensure we actually get different random numbers each time a program runs. The function time, when it's given the argument null, is going to return the current time. Because the current time is always going to be different, we're always going to be seeding the random number generator with a different time. So now that we've done that, we're going to actually generate the random number, knowing that it's going to be actually random. So in here, I'll say int pivot index is equal to low plus rand modulus high minus low. So what we're doing here is generating a random number between low and high. So the rand function is going to return some random number, some random integer between 0 and some very, very high integer value. What we want to do is put that in the range of low to high. What we're doing here is taking that number and doing a modulus of high minus low. And then we're adding to that low. And what this is going to do is give us a random value in between low and high. The next thing we're going to do is swap whatever is at this pivot index with whatever is at array high currently. And then the rest of the algorithm can just proceed as it was before. So we'll say here, if the pivot index doesn't already equal high, then swap whatever is in the array at that pivot index with whatever is in the array at the high index. And this will just make it so that we take that pivot value and we just put it in the last element of this portion of the array that we're considering in the index high. And then the rest of the algorithm just proceeds as usual. So we can save this and run it. And it's not actually going to affect our result. We'll still get the same result. We've just made our algorithm more resilient to cases where picking the high pivot every time is not going to be efficient. And so this is how we can implement Quicksort in C. Check out portfoliocourses.com, where we'll help you build a portfolio that will impress employers, including courses to help you develop C programming projects.